My name is David Reed. I'm a senior member of technical staff at Salesforce.org, where I work on the release engineering team for NGO products there. I hold 8 Salesforce certifications. I work mostly in Apex and in Python. And one of the things that I'm most passionate about in the development process is testing, automated testing, all species of testing to make sure that we're delivering good quality software everywhere that we do so. Part of my project today is to share some of that passion with you and hopefully let you see why testing can be really an exciting process and not just a chore you have to complete. I don't plan on making any forward-looking statements today, but please do remember to make your purchasing decisions based on what's currently available. And let me give you a quick overview of what's going to be in this talk. There's a lot that I'd really like to cover, so I am going to talk a little bit fast. I'll give you just a heads up that at the end of the presentation, I'll be sharing some links, and one of those will be a GitHub repository where you will be able to see all of the code that I'm going to demonstrate for you today. You can download that yourself. You can run the unit tests. You can experiment with it, make changes, and so on and so forth. We're going to start today with a discussion of how we frame testing objectives, what a testing program is all about for us. We'll dive into some testing strategies for what I'm calling real code that might not be perfect. So if we don't get to make nice assumptions like we're working in a perfectly heterogeneous org that's been built by, or perfectly homogeneous org that's been built by one person with all the best enterprise design patterns used throughout, we really have to get nitty-gritty with our code and understand how to test these different Apex constructs that we might be using at a very low level and in a very concrete kind of way. I'm not going to talk a whole lot, despite my title, about how to obtain code coverage, and there's a reason for that. And what I want to start with is an attempt to persuade you that talking about code coverage is actually the wrong way to frame a unit testing program or a testing program more broadly. And lastly, we're only going to be talking about Apex testing today. Apex is one component of a broader testing program that you might have in place that could include front-end testing, user acceptance testing, regressions, and all kinds of other pieces. But here we're going to focus on the Apex angle. So let's start with code coverage. We all know code coverage because it's a required metric that's set by the Salesforce platform. In order to go to production with code that you've written, you must cover 75% of the executable lines of code in your classes and triggers with a unit test. Otherwise, you will not be able to deploy. That's a blessing and a curse. It's a blessing because it forces us to write tests, which we should be doing anyway. It's a curse because it focuses our attention on this metric, code coverage, when we think about unit tests. And code coverage can be a bit of a trap. If you're looking at the code I'm presenting to you here, you've probably already spotted one or two issues. What you might not realize just from inspection is that this unit test I'm showing you here yields 100% code coverage of this trigger. But the trigger is broken. It's completely broken. You couldn't possibly deploy this to production because it doesn't work in a couple of different ways. The task it inserts isn't connected to anything, and it only acts on a single object on every single trigger invocation. But it's covered at 100%. That's because code coverage is a proxy. It's a machine-readable proxy for how we are testing and how broadly we are testing our code. It's useful and it's important because it allows the Salesforce platform to look at our deployments to production and decide whether we have done some minimal level of effort to validate the behavior of our code. But it's not the be-all and end-all of evaluating tests. In fact, far from it, it can actually be harmful if you focus too much on code coverage because you end up in situations like this, where you're optimizing for the wrong quality and you miss real bugs in your code. So here's how I want to begin. Optimizing for code coverage is the wrong goal for a testing program. If we follow a better goal, we'll get our code coverage for free, and we'll get it at or very near 100%, not 75%. And if we shift our focus to a different center for our testing program, we can use code coverage as a tool rather than a guiding star to help us identify deficiencies we might come upon along the way. Here's how I do want to frame a testing program and the process of building tests for our code. Testing is a promise that we are making. Specifically, we're claiming two things about the code and tests that we are bringing out of our development process. One, when the tests pass, the code works. And two, just as importantly, when the code will or would fail, whether that failure has to do with flaws in the code itself, changes in its input, or changes in the environment around it, the tests will also fail, giving us a warning that there's something wrong that needs to be corrected before faults occur and become expensive. When we make that promise, we're actually offering it to quite a lot of people. We're promising ourselves as we continue to work on developing our software. We're promising our colleagues in IT. We're promising our business users, customers, and clients who depend on the code that we write to get their jobs done and to make money. And we're promising our leadership. The stakes to those promises that we're making are pretty high, and that's one reason why it's so important to take them seriously, and why I feel it's important to frame testing as a person-to-person, a sort of moral imperative, more than the technical imperative of a code coverage metric. We're staking a lot of money on the software that we build at many companies, at many nonprofits as well. Millions of dollars flows through the systems that we build. And we're also staking quite a bit of trust. When users lose trust in us, in the work that we do, in the data in their CRMs, that too can be a very expensive problem, but it's also a moral failure. So if we're framing testing as a promise that we're making and we want to keep that promise, how do we do it? How do we make these promises meaningful and ensure that we're in a position to keep them both now and in the long term? Well, we need to hit a number of marks with our tests. They have to be comprehensive. They have to cover all of our software. They have to be effective and make claims that are verifiable about what our software is doing. And they have to be representative of real use and failure scenarios. If we're only testing things that are highly abstracted or that don't reflect the way our software is actually used, the results of those tests may not bear upon how our software will perform when it's used in production. So those are some reasons why I think testing is very important and why we need to put the center of our testing program at that idea of a promise, a commitment that we are making. As one more element of persuasion, I want to try to expand our view of the lifespan of a unit test. It's easy to get stuck thinking about a unit test as something that you run once and then forget about. You run it when you're deploying to production because you have to run it when you're deploying to production. But that's really the starting point. Let's say you're an organization that continues to develop the same Salesforce org for many years. Your code might be in production use for 4 years, let's say. It could be longer, it could be shorter. Your organization is using an agile development methodology. You deploy to production every 2 weeks, and you run tests in sandboxes and other pre-prod orgs at least 3 times before you go to production. Well, simple multiplication, that's 416 times your unit test is going to run in its lifespan. 416 times that it has an opportunity to catch a regression and a fault or a bug before it gets to production. 416 opportunities for you to protect your users. That's pretty important. These are really good reasons for us to write high quality tests that work well and validate our software. So let's dig in on how we actually do that. There's 3 key pieces to every unit test, as we've probably seen before. Piece 1 is environment setup and data creation. That often takes place in a test setup method like the one I'm showing you here. This is how we control the environment around our code as we prepare to test it. That makes sure that our tests are repeatable and reliable. They give the same result every time. The second piece is the execution of functionality, which takes place in a unit test method like this one. We put simply, we call the code. We make it run in the context that we've established. And the third is we make meaningful assertions about what that code is supposed to do or is supposed to not do. This is the meat of our test. This is the validation piece where we make sure that the results are as they are expected to be. Unit tests that don't contain assertions are often called smoke tests because they don't really tell you anything except whether there's smoke coming from under the hood. If the engine's fallen out, that is important for you to know, but it's also important to know that the engine's running within expected tolerances. That's why you make assertions. Unit tests come in a number of different flavors as well, and it's important to cover all of these different flavors when you are building a new piece of software because not every user interaction goes down what we might call the happy path. The happy path is what we usually test with positive tests. A positive test is one where we just say the code does what it's supposed to do. It does what it says on the tin. We give it good input and we get good output. Well, GIGO, as it's often used in software engineering, doesn't mean good in, good out. It's garbage in, garbage out. So the positive test is really just one piece. And it's often the easiest piece to construct. Because of the way that Salesforce works as a platform, we might have a few variants of a positive test. We might test on single records, on multiple records, and on high volume, like a 200 record unit test if we have the ability to do that. But fundamentally, what we're saying is the code works, and it does what it's supposed to do. That's one piece. But another piece is the negative test. A lot of times we'll find when we take our code to production that users interact with it in ways that we never saw coming during the development process. And one way that we can guard against those dangers is by writing effective negative tests for the various different kinds of things that could happen that do not fall on that happy path. That could be what happens when your code receives a null parameter. when it receives an empty list, when the user does not have permission to access a specific field, when data that's queried from the database does not have the expected structure, when a validation rule has been disabled, for example, and you don't meet established invariants. All of those things are negative cases, and the behavior of your code needs to be tested to ensure that when one of those unpleasant occurrences takes place, your code's behavior degrades gracefully. And the logical paths that you've put in place to handle those situations work the way that they're intended to work. Here's a couple of quick examples of negative tests where we're validating what happens when we call code with a null parameter, or we're checking to be sure that an exception is thrown when we expect an exception to be thrown. There's another species of negative tests that I call no action tests. And these are tests that validate not just that code does what it's meant to do and handles errors the way it's supposed to, but it also doesn't do what it's not supposed to do. And what I mean by that is, take a trigger, for example. A trigger operates on the opportunity record to populate a custom field with an industry value from the account. But we don't want to overwrite any value that's already been populated by the user. That's an instance where we'll use filtering logic or criteria in our code. We have to make sure that those criteria are applied correctly and that we're not touching records that we're not meant to be touching. That's what I mean by no action. We validate that our code does not act when it is not intended to act. This can often be joined up with a positive test. The example I'm showing here is basically a positive test, but I've added an additional record in my data setup that I don't want my trigger to affect. And then as part of my validation step, I look at that one record and say, I'm validating that my trigger has not made any changes to the data in this record. That's important because the data that you'll see in the environments where you're doing your software development, like scratch orgs in particular, don't have the kind of data that you'll see in production. You'll see very different looking record structures, maybe even different data models or invariants being violated. And you need to make sure that those criteria you put in place are going to be followed when you go to production, lest you risk damaging your company's production data. Lastly, you might look at permission and sharing tests. This would be a situation where part of your data setup is creating a user environment, a user, some permission set assignments, a role, for example, in the role hierarchy, and ensuring that your code behaves effectively in different user contexts. Users who can't see specific records, users who don't have a particular custom permission, allowing them to take one action or another, and so on and so forth. Permission and sharing tests are one of those which will be most org specific. So you can't necessarily give a canonical example here. If you're an ISV, this will be particularly important for you, but even end users need to write these kind of tests as well to ensure that they're not using system mode in Apex to violate the permission structures they've established. Writing good tests is one piece of the puzzle. And we've looked at some precepts for doing that. There's several different kinds of unit tests we need to write. There's several elements to a unit test that we need to establish. But the other side of the coin is the code that needs to be tested itself. And we can follow some precepts in building our code to make our job considerably easier as we actually go to build those tests. You may be thinking, as you hear me step through 4 or 5 different kinds of unit tests, how on earth do I actually write that many unit tests for this large suite of code that I'm preparing for my product? Well, I want to go through a quick exercise here to look at the connection between the structure of the code you're testing and the unit tests that come out of that. And then we'll go through some strategies for simplifying the logic of code, making it easier to test, more streamlined, and allow you to complete that testing process more effectively and more quickly. So this is a piece of code here that's intended to be called from a trigger running on the opportunity object. It's taking action, as we mentioned earlier, to populate a field called priority on the opportunity based upon the industry of the associated account. And this code's a little bit messy. If you look at it here, you can see the logic is nested kind of deeply. We've got a lot of if statements. We've got a lot of different outcomes that could come from this code. So what I'm going to do here is step through pathing this code, understanding the different routes through this method as it's being called with different kinds of input, and see how those different code paths map to unit tests, given that we might have a roughly one-to-one analogy between a code path and a suite of unit tests that validates the behavior of that specific path. Let's start here. Suppose we pass an empty opportunity list to this method. We start at the for loop here, but because our list is empty, we never enter it. That's one code path. We have to know what our code does in that situation. Try again. We'll pass one opportunity. We enter the list this time. We start evaluating this logic, but that record doesn't meet criteria to take this first action here. That's another code path. We need to know what happens. We keep stepping through the logic. This is how we're building a path. You see our flow of execution touches each of these logical branches as we move through with different data input. This time, we enter with an opportunity that does match our first if, that does have an account associated with it, and we look to see whether it's got the right industry to continue moving through this code path. It does. But we're not in the right mode to take action here, so our code path ends there. Again, we need to validate that path of action. If you're doing math in your head, again, you're looking at, I've built up 4 code paths here. We talked about 4 or 5 different kinds of unit tests. That's starting to be a lot of work for us to do to effectively validate the behavior of this code. And it gets worse, right? There's another path where we actually enter this final if statement. We take action. We populate that priority field with a prioritized value. That's another code path. And another, and another, and another, and another, right? This is getting very messy. So one of the key strategies for building testable code is to write code that's easy to path, where we don't have to do quite as much work as we just did to figure out what's going to happen when we call each particular unit of our code. Some of the strategies that go into that are factoring and modularizing our code, reducing cyclomatic complexity, which is a measure of the depth, the branching complexity of your logical tree, the number of pathways through that code, and remove and flatten unnecessary branching logic. And as our first example, I'd like to actually do that or show you how I've done that with this particular piece of code. So I'm going to swap over to my IDE here. Can you all see that all right? So this is the original piece of code that I showed you here. This is an opportunity service class. It's about 46 lines long. And again, you can see there's a lot of convoluted logic here. It's too deep and it's repetitive. It's redundant. If we look over at version 2 here, what I've done is I've gone through and refactored it, and I want to focus on this section here. I've refactored it. It's a little bit shorter. I've pulled out a unit of code into a separate method to get a priority value based upon a dollar amount. That doesn't need to be part of this big, long method. It's a separable unit of code that I can isolate. And I've streamlined the logic here, so I've only got 2 levels of if, and I don't have a long if-else chain. The number of code paths that I need to worry about here as I'm unit testing just shrunk dramatically. And I will show you that as well. This is a unit test, or a couple of unit tests for the original class. I've got 3 unit tests here, 64 lines of code. These are positive tests only, and they're positive tests only for the first couple of code paths that we looked at. They obtain 27% code coverage. Here's some new unit tests. It's not much more code. It's only about 20 lines longer. So we're not looking at double or triple the amount of code here. These are tests for the new factored service class that's much shorter, flatter. Again, we're only looking at positive unit tests for this quick example, but these unit tests that are only 20 lines longer get 100% code coverage instead of 27%, just by virtue of having done that factoring exercise to flatten our logic and streamline the flow of control through that code. So that's our first example here, how to approach code from a testing perspective to make the process of building those high-quality unit tests a little bit easier. And again, please see the repo on GitHub for the full code here that we're using. Another piece that we're executing here that's going to be our second example is thinking about the code that we're building from a testability perspective by viewing our unit tests as a consumer of the API that we are building. When we define a class like this, we're defining an API that's going to be consumed by some client or another. In this case, it's envisioned as being a trigger. Well, our unit tests are a consumer of that API too. And thinking about our unit tests as an API consumer gives us an opportunity to do this factoring work and also to think about whether there might be changes that we can make that increase the testability of this code, that also increase its viability as an API. Some of those changes that have been made here are, as we discussed earlier, pulling out an element of code and promoting it to an independent method. In other situations, we might take that even further by promoting that method to a piece of public API, either as part of this class or by factoring it out into another handler or service class where it can be used by more parts of our application, and where it can be tested in isolation as a separate code unit from what we're working on here. In this case, we'll expose that method just to our unit tests using the test visible annotation. And we can do the same thing with state. When we're storing state within our class, we expose it to our unit test as part of our testing-focused API to make sure that our tests have access to all of the elements within that class that we're building and can effectively test their behavior. That's leading up to one of the more advanced topics that we'll get into in unit testing, which is dependency injection and mocking. And I want to take a brief interlude here to explore that particular technique, because the last part of this presentation is going to be an exploration of some more complicated unit testing scenarios where we have to get into some really complex code, some asynchronous code, and figure out how to validate its behavior effectively. Dependency injection is a tool that we're going to use there to allow ourselves to evaluate those code paths that are really hard to get to because of some of the ways the Salesforce platform works. Dependency injection is a way to help ourselves get better isolation for tested code. This is that first element of those 3 elements we talked about of every unit test. Create your data setup, create your environment setup, isolate the code under test from everything else in your org, from all those potential SKUs. Dependency injection is a way that we do that. We isolate external dependencies of our code, like SOQL queries against custom metadata records, callouts, calls to the Chatter API, other things that we have difficulty controlling through simple DML setup. And we pull those out into helper or utility classes, which we can then replace with a testing substitute as we're running our unit tests, allowing ourselves to use those mock classes to return controlled, standardized data and make sure that we get into those code paths in a reliable and repeatable way. There's several different ways to implement custom dependency injection. I'm going to show you an example here of using dependency injection to mock a custom metadata query. And we're going to do that using an interface-based strategy. There are other strategies you can use, applying stub provider or using inheritance. All of them have the same rough structure. This is just one way to execute it effectively. And here's what the main elements look like. First, within our main class, and again, this is this opportunity class that we're talking about, we're going to define a private interface. Here it's called IOpsServiceQueryDelegate. It only has one method. It returns a list of custom metadata records. As you may know, if you're building a unit test, custom metadata is visible to your unit tests. It is not considered data, it's considered metadata. That's a potential external dependency for your tests that can prevent them from being effectively repeatable. Secondly, we'll declare a custom subclass, an implementation of that interface within our main class, which provides a concrete implementation of that interface, and we assign an instance of that class to a delegate variable, an instance variable within that class. This is basically boilerplate, and the reason that we do it will become clear in a moment. In the test context, we're going to implement that same interface again. But instead of doing the real action that our code will execute in production, like running a query, calling the Chatter API, or even making a call out, we're going to substitute a mock that returns standardized fake data that we can use to control the entry of our code into specific code paths. Here, we're returning a custom metadata record that we create in memory. In Apex tests, you can't insert these records, but we can do it with a mock class like this to make sure that we always have the same data set available to our unit test. And then the coup de grace. In our unit test itself, we create a new instance of opportunity service, and then we perform the injection. We'll create a mock query delegate in our test context, and we drop it in by populating that delegate variable there, so that here and only here, in the context of this unit test, our code will not run a real query against custom metadata, or it won't make a real call to the Chatter API, or it won't make a real web service call out. It will use a mock instead, and we'll get back that controlled data to establish our test environment. And then lastly, we validate the behavior of our code based upon that expected input. We're going to use that in several different ways when we look at these advanced testing strategies. So the big questions that we have to ask when we're looking at how to unit test complicated code, difficult code, like batch classes and multi-layer asynchrony, queuable chains, that kind of thing is, one, how do I execute this in a test? How do I create the conditions to make this code path run when we're talking about some of these built-in platform functionalities that aren't just controlled by running DML? And two is, how do I control the test environment? That's where we use the mock to bring in that standardized data. So I want to look at a few different examples of where we'll use dependency injection, and then we'll wrap this up and hopefully have time for a couple of questions. One is exception handlers and failure paths. Sometimes it's easy. Just pass null, you get an exception, you validate that you got an exception. Sometimes it's hard. You can't create a row locking exception in a unit test, at least not intentionally. That can happen. So this is another situation where you'll have to factor that query out, and you'll use dependency injection to force a query exception to be thrown. Otherwise, you can't get into that catch handler in your unit test. You'll never validate that behavior. Complex asynchronous code is one of the places where you'll use dependency injection most heavily, but it's also one of the places where it's most difficult to use it well. And that has to do with how the platform works, some of the inherent limitations around what we can do. Test.stop test, as you might know, only supports one layer of asynchrony. So if you're testing a scheduled batch class, that batch class will not run just because you scheduled your schedulable within a unit test context and then called stop test. It won't happen. You have to decompose that functionality and test your asynchronous units separately. They can't chain into one another. Likewise, you can't chain queuables and batches in a test. You can't run multiple batch invocations. And because asynchronous code is serialized before it's executed by the platform, it's much harder to perform dependency injection because you lose your reference to that mock class, to your delegate when you inject it, between the time when you schedule the batch and the time when it's actually executed. You won't have access to that internal state because the running class is not the same instance of that class as the one that you're holding in your unit test. That makes it much more difficult. That assertion that I'm showing you there will fail. So we have to use different strategies instead. And we have to be pragmatic about it from time to time. One way to do that is to call the execute method on something like a queuable or a batch class synchronously. That'll allow you to use dependency injection because you take away that layer of serialization and asynchrony that's managed by the platform. You're just running normal synchronous code, and you still have access to internal state that you can validate. Another is to take your multi-layer asynchrony apart and test it piece by piece in isolation. You don't get that luxury of running those end-to-end tests that you might want to run. And lastly, again, you can factor your code. Pull your logic out into a helper class that you can test synchronously, and then call it from your asynchronous code, your batch, your queuable, or what have you. There's other challenges where we'll use dependency injection. Connect API is one of them because you need CL data equals true. Outbound callouts are another where the platform gives us really good support for using mock classes. And before we close, I want to go back to code coverage one more time because ultimately this is a strategy that will yield us code coverage, as we talked about at the beginning of this presentation. My takeaway message, if you leave with nothing else, is this. Testing is not just about writing unit tests, and it's not just about chasing code coverage. It's about building well-structured testable code as well. And if we do that, and we do it well, and we write quality test code for each of the distinct code paths that we've established, we'll get 100% code coverage for free. We won't have to worry about it. We won't have to chase it. And that's the point at which we can use it as a tool rather than a hobble. If we don't get that 100% code coverage, we know something's wrong, and we can go look at what that might be. Thank you. As I promised, I'll leave you with a few links for resources, and I'll just highlight again that the code for the examples that I showed during this presentation is in a GitHub repo that you can play with. You can run the unit tests yourself. Just as a caveat, that doesn't represent an example of a perfect unit test suite. It's just positive tests, but it's an example of how to use factoring and flattening of your code's decision tree to write better unit tests more efficiently.
Thank you so much, David. So we have a few minutes for questions. Does anyone have any questions for David? Maybe a shout out again on that quick.
Hi, David, thank you. Is there a benefit or a way to have scheduled tests run in production work? Would that help identify potential issues that might crop up in the bad unit test or configuration or code?
Run your Apex tests on a scheduled basis in your production work. Yeah, there's a couple of different ways to do that. And it certainly can be beneficial if you're an org that permits declarative changes to be made in production. One of the places that I see unit tests fail all the time is validation rules. You don't have to run your Apex tests to deploy a validation rule in production, even if you have to test in the sandbox. If you're in order that allows that kind of change to be made directly in production, you might find some value in running your Apex unit tests on a regular schedule, because those kind of declarative changes that can have code impact will be caught early, hopefully before they create impact to your business or your data.
The process builder and with triggers, so do you recommend writing test classes to transducers to are they able to add those software query headers and things like that?
That's a really good question. And to be honest, I have fairly mixed feelings about unit testing process builders and flows. The platform has pushed us a little bit to do that. As you might know, we can now deploy process builder flow automation in an active state if and only if we provide code coverage of a sort through unit testing for those automations. So that's an impetus for us to build those unit tests. I have worked on projects before where we were asked to build unit tests for workflow rules. I don't think that's a good idea. It may be a good idea in some specific orgs, I should probably say. That's probably too broad a claim to make about every single development process. But my feeling is if you are working in a context where you're building declarative automation with the intent that an admin should be able to maintain it and make changes to its behavior in the future, you do not want to lock that org into the exact behavior you establish at deployment time by writing rigid Apex unit tests that will fail when the admin makes those changes that you're designing your solution to allow for.
Where else can I find you? Have a dev blog or anything I can follow you to see more good stuff?
Yes, I have a blog at I'll have to spell it, ktena.org. It's me. You can find me there. You can find me on Twitter. You can also find me a lot on Salesforce Stack Exchange.
David, what's your take on developing and writing tests always for bulk, if not writing for single record cases?
That's a really good question. I don't have a hard and fast answer for every case. If someone says you should only write bulk Apex tests, you do not need to ever write a test that inserts only one record, I would be prepared to buy that most of the time. I have once or twice, I counted on the fingers of one hand, seen bugs where it is possible to create an issue by passing only one record in a situation where it won't happen with more. I think that's extremely rare. And if you want to build high quality bulk unit tests only, I would consider that generally an acceptable practice.